My name is Suhabe Bugrara. I'm a PhD student at Stanford. This is joint work with my advisor, Dawson Engler. This talk is about redundant state detection, which is an optimization we've developed for a powerful technique called dynamic symbolic execution. With this optimization, we're able to speed up symbolic execution on average 50 times. So dynamic symbolic execution is a technique that allows you to systematically explore every program path. It's capable of being fully precise because it's able to track every variable and every value for every variable on every path. It has many applications such as automated test case generation, malware signature generation, equivalence verification, assertion checking, memory safety, and patch checking. And it's also been heavily researched there's a number of research tools out there. So just to give you an idea of how this works, consider the following code example. So symbolic execution starts with an initial state. So here it represents states as these blue boxes. You'll notice that this function has an input argument I, and the way we're going to represent that is by adding this constraint I equals star. And what this means is that I can be any value. And that makes sense because I is an input argument, and we want to explore the behavior of this function for any possible inputs. So symbolic execution works by starting at this initial state and then executing every instruction on that initial state. So here, for example, the first instruction assigns or initializes this array A. You can see now we've added this constraint to the state in addition to carrying over I equals star. From now on, I'm not going to include A into these states because just to avoid the clutter on the slide. So now is the critical step with symbolic execution. We've reached this program point if I is greater than or equal to 3. And what's happened is that the state has split into two different states, one in which the condition is true and one in which the condition is false. You can see now that also these constraints have been, the constraint on I has been updated. On the true branch, its constraint to be greater than or equal to 3, and that makes sense because it's on the true branch, obviously. And similarly for the false branch. So let's start with the true branch. Now it's reached this exit statement. And as soon as a state reaches an exit statement or end of the program, what we do is we look up the constraints in the state, we solve it. For example, I equals 7 is a possible solution to these set of constraints. And then we terminate the path. So what's happened here is that we've explored this path to completion, and now we're generating a test case. So this is how symbolic execution is capable of automatically generating test cases for your program completely automatically. So now that that state's done, we move on to the other state. Now it's executing this assignment to T. Now, there's one issue with the statement is that there's a potential buffer overflow, and what we want to do is check whether there is one or there isn't. So the condition under which there is an overflow is when I is greater than or equal to 4. Next, symbolic execution will try to solve the path constraints again, and it will find that they're infeasible, that there is no solution to this set of constraints for the variable I. So this allows us to conclude that there's no buffer overflow, and we terminate the path. Then move on to the other state in which A of I is a safe access. You notice here that we incorporated a constraint on T. Notice how we were able to evaluate A of 3 to a concrete value 2 simply by looking it up in the array, whereas we left A of I as it is, as a symbolic, what we call as a symbolic expression. And this is an example of the power of the technique, is that it's able to reason about these accesses to arrays by indexes that could take on a range of different values. Next thing that happens is, same as happened before, is when we reach this if statement, we again split into two different states. And again, we eventually reach the return statement on the true branch, and we split again on this second if statement. So the thing to take from this slide, or there are several things to take from it. First is that we're able to systematically explore all possible paths for all possible values of I. We're also able to generate test cases for every single path by solving the constraints in the state. And the other key thing to note is that every if statement, we've split the state into two different states. So this is what leads to the state, what's called the state explosion problem, and it's one of the biggest challenges for symbolic execution. So the problem is that every if statement, again, we split into two different states, so this generates obviously an exponential number of states, and therefore it inhibits the scalability. Here, for example, this graph shows how states are being generated over a period of 1 hour for the common utility called makedir. See, it's chain race up to 90,000 states in under an hour, or almost 90,000 states in an hour. And if we just let this go for longer, it will eventually just run out of memory and crash. So we've developed an optimization called redundant state detection that tries to address this problem. The key insight is that we prune states that must execute identically to a previously explored state. So for example, if your goal is to produce high coverage test case generation, we prune states that do not reach new lines of code. So the challenge with this, obviously, is that if we're executing a state, we don't know in advance what lines it will cover. And the approach we take to overcome this challenge is to compare the state, as we said, to previously executed states to see if it definitely does not cover any new lines of code. So to give you some intuition for how this works, consider these two states. They have the same set of constraints. As you can see, x equals 1, y equals 2 in state A, and x equals 1, y equals 2 in state B. And these arrows coming into the state just illustrate that these are coming in from two different paths. And they're coming into the same basic block of code. So that's an important point here because we can't compare states unless we're at exactly the same line of code. So again, as we said, the constraints are equivalent. So what can we conclude from that? We can conclude that state B will cover the same lines as state A. So this is great because if we find that this is the case, we can just get rid of them and not have to worry about exploring it. And that saves up a lot of, that allows us to avoid doing a lot of extra work. Now the problem is that there are very few states that have entirely equivalent constraints. I mean, these two states happen because they follow two different paths. So it's almost always going to be the case that they're different. So we take a different approach. Here, for example, the more typical case where we have a state A and a new state C that differ on the variable y. Again, they're coming from two different paths to the same basic block. And again, the different values of y. So what can we conclude from this? That state C may cover different lines than state A unless variable y does not affect whether state A reaches an uncovered line. And this is the key point. If we're able to show that y has no effect on whether A was able to cover a new line or not, then we can ignore it when we compare state A and state C. So again, the key question is, does the value of y affect whether state A reaches an uncovered line? So let's make this more concrete. Instead of that basic block of code, let's use these three statements here. It's very simple, z equals y, if z, w equals 1. You notice these check marks on the first two lines, and we use, throughout the rest of the presentation, we use check marks to indicate which lines are covered and which ones aren't. So here, the first two lines are covered, and w equals 1 is not covered. So our goal is to try to get down to w equals 1. So the question before us is, we want to try to get rid of c, and we want to find out whether we can do that even though even though they differ on the value on the variable y. So let's suppose that state A takes the path that hits the first two lines, but then takes the false branch on the if statement. So we tried to illustrate this with the arrow kind of curving out. So it's a path that hits z equals y, then if of z. Now you notice that obviously z is the same variable here. And the key part in the slide is this relationship between z and y. This is what's called a data dependence. So what we see from here is that the value of y does affect whether w equals 1 is reachable, because its value leaks into z and then leaks into that if statement that controls an uncovered line. So as a result, we have to conclude that variable y does affect whether A reaches an uncovered line. Now there's another situation in which we have to conclude that we have to compare y when we look at two different states, and that's control dependence. So again, w equals 1 is the uncovered line, and the rest of the lines have been covered. So we'll see that the assignment to z of 1, or the assignment of 1 to z, is controlled by if of y. And the problem here is that if depending on what the value of y is, z equals 1 will be executed, which will also in turn affect whether f of z is executed. So we also have to conclude that y does affect whether A reaches an uncovered line. And there's one last situation in which we have to track y, and that's implicit dependence. This is a slightly more difficult one to grasp. In fact, it requires a sound static ALE analysis to compute properly. But basically, it's similar to the idea of information flow, where you have these kind of implicit flows of information between branches. It's the same kind of concept. You'll notice actually it's the same example as the previous slide for control dependence, but the key difference here is that A is taking a different path. It's not actually executing z equals 1. And as a result of that, we have to be able to reason, as we're reasoning along the path, we have to also consider parts of the code that have not been executed on that path. And that requires some static else analysis. So just to quickly summarize, there are these three kinds of dependencies between variables that we have to worry about to determine whether a variable affects whether a line is going to be covered or not. So let's see how we actually use these dependencies to carry out the reasoning to determine whether state A and state C are equivalent to each other. So here, suppose state A reaches or executes entirely to completion. That means all of its children eventually reach the end of the program. So the first thing we do is find out where the uncovered lines are and the branches that control those uncovered lines. Then along each path from these uncovered lines, we track all the dependencies between variables. And if we determine that after we calculate these dependencies, what we want to do is see whether variable y is included as part of these dependencies. So if it's not included as part of these dependencies, then we can be sure that it's not relevant and we can ignore it. So here, suppose y is not part of the dependencies. Now, what will happen is that you'll see that we faded by y equals 2 because we're assuming it's not relevant here for the sake of this example. And then we're fading out y equals 3. So because y is not part of these dependencies, we can compare state A and state C just on this variable x. Now they have equivalent constraints, and we can just prune them, or just prune state C. So to make this a little bit more concrete, consider like this very, very simple code example. The reason we kept it so simple is just so it's clear what's going on with our optimization. So again, it's two simple if statements. Either you print x or y, or you exit with 0 or 1. So let's start with this arbitrary initial state that I just pulled out of thin air. W equals 1, m equals 1. And we're just going to execute it, just straight symbolic execution, nothing fancy. Just evaluating it until it reaches this exit statement on line, this exit statement that exits with status 0. You notice again the check marks on the left indicate that the line's been covered. So our goal here is to get check marks on every line, so we want 100% coverage. Now let's pick another arbitrary state. The only difference now is w equals 1. Again, we're going to execute it. Notice that now we just covered this print x here. And similarly, a third initial state. Now notice that it'll do exactly the same thing as the second initial state, and I'll get back to that point. And then finally, this fourth state where w equals 3 and m equals 0. And now we've covered all the lines of code in this example. So this is normal symbolic execution, how it would work in normal situations. So the thing to note here is that there's a lot of redundancy. Like, we're doing way too much extra work. We should be able to see that we've explored this behavior before and that we don't need to keep doing it. And here's another example of the redundancy. So let's see how symbolic execution would work if we're running our redundant state detector. So again, we start with the same initial state. It's just executed the same as before, nothing's different. And now the key part of our optimization will be shown. So now, as soon as a path terminates that reaches an exit statement, what will happen is that we first identify the if statements that control uncovered lines. So here, you'll see here that if of w controls an uncovered line because print x hasn't been covered yet. And also, if the if statement, if m, also controls an uncovered line because the exit at the bottom hasn't been covered yet. So these are what are called relevant static branches. So in order to identify which of these constraints in these states are relevant, we start at the last state that was just executed, that terminated, and then we go backwards. So it'll look like this, for example. So you'll see that. So the first question is, what are the relevant constraints in this last state that's terminated? It's trivially empty. There are no relevant constraints because this is the last state, and there's nothing else to be done. But then the second to last state, m equals 1 is relevant because the if statement, if m is relevant, that it controls an uncovered line. So in other words, this constraint will affect whether we reach the last exit statement or not. So we have to track it is relevant. And same thing for the rest of these states. Now this first state, the only difference here is that now w equals 0 is also relevant, again, because it controls this uncovered print statement at the top. So now we've identified all our relevant constraints. Again, let's start with the second initial state. This is the same one as the same initial second state as the previous slide. And the first thing we're going to do is we're going to compare this state now to the previously executed state, the first initial state. Now, unfortunately, we can't conclude that there's a match here because they differ on the variable w. In the old state, w equals 0, and in the new state, w equals 1. So we can't prune there, so we have to keep executing. So we move on to we continue executing this state until we cover this print of x. So this is another key point in this slide, is that now once this line is covered, this if statement, if w is no longer relevant. We don't have to track it anymore because it doesn't control any uncovered lines. So what that allows us to do is to go back to this initial state or the first path that we already executed, and we can now get rid of w equals 0. We don't have to track that anymore. And we'll see why this is valuable in a second. So now we continue executing. Again, we compare. Notice here that in this state, w is not relevant. So there is a match, and we can prune the state. We can avoid executing this other state down there. Now, again, we pick this third initial state that we looked at before, and we do a comparison. Now, the key point here to note is that just a second ago, w equals 0 was relevant, but because our analysis was able to automatically infer that after covering print x, it's no longer relevant, now we're able to prune this state. So I'll go through that one more time. So you'll see that w is not relevant here, and they agree on the constraint m equals 1. So we can completely prune that state and not have to worry about it. So the rest of these aren't executed. Now, one last point. So again, this is the fourth initial state. If we compare it again, the same process, compare it to the previously executed state, we find there's no match. Again, we find there's no match. There's a disagreement on m. And then we finally were able to cover the last two lines. So this is really important because the important characteristic of our analysis is that we're sound. We don't prune states unless we're absolutely sure that it's not going to cover new lines. So this is not a heuristic. So there are a number of other novel techniques that are discussed in the paper that I'm not going to have time to discuss now. For example, there are these complex dependencies called irregular control dependencies that show up when you have embedded halts. So these are just like exit statements that occur randomly in the code or at arbitrary points in the code. The other interesting technique is that we have this ability to alternate between unsound and sound detection. So this is one of the unique situations, or one unique situation in which unsound and sound analysis are synergistic. It's actually almost never the case that this is true. The way we leverage these two different analyses is that we use unsound pass to hit the easy lines of code, and then use a sound pass to prune the states. Running an unsound by itself or running sound by itself won't give optimal results. It's only when you combine them simultaneously. Another technique is the use of decision trees to compare states. So we've looked at the examples we've seen in this talk were very small, but as you'll see, like we actually ran this on real programs, and for those large programs where there are tens of thousands of lines, what ends up happening is that there are thousands of states at each program point that you have to compare against. And doing a straight linear comparison between these states is just not going to work. So what we've designed is these decision tree-based data structures that allow us to efficiently check whether a state matches another state. And there's other two techniques which I won't discuss now, but they're discussed in the paper. So I'll discuss how we evaluate our technique. We used CLE, which is a symbolic execution tool that was presented in OSDI of 2008. So CLI-base is, I'll refer to the open source version of CLI as CLI-base. And this is configured to use its best built-in heuristic search strategy for code coverage. And CLI plus our redundant state detection, I'll refer to that as CLI-reduce. So we ran the same experiments as the original CLI paper. These are the benchmarks that we ran against. These are probably programs that you've used quite a bit. So these are the GNU core utils. So just to give you an idea of how big these programs are, even though they may seem small, they're actually very large programs because they pull in a lot of library code. Here you'll see that almost all of them have more than 10,000 instructions of optimized LVM code. So the way we calculated the speed up to see how effective our optimization was to run each program for 1 hour with CLI-base and CLI-reduce. So Cmax is the maximum coverage that both CLI-base and CLI-reduce are able to reach. T-base is the time it took CLI-base to reach Cmax. And T-reduce is the time it took CLI-reduce to reach Cmax. And the speed up is simply T-base over T-reduce. So here are our results. Notice that this is a log scale. So what this means is that on average, this optimization speeds up symbolic execution by 50x. And the median is 10x. What that means is that at least half of these benchmarks have an order of magnitude speed up. So again, this is not, the median shows that these aren't outliers that are skewing the result. There's a maximum speed up of 700x and a minimum of 0.2x, which is actually a slowdown. And I'll discuss those in a little bit. There's also another important measurement, which is termination. So on 12 benchmarks, our optimization was able to prune enough states to the point where it exhausted the state space. And what that means is that, essentially what that means is that all uncovered lines after it's terminated are provably dead code for any input arguments with respect to the given environment. And that's an important point. So here are the coverage increases. The maximum coverage up to almost 30%. So in these benchmarks here, where there's no coverage increase, CLI-base reaches the max coverage anyway, so we can't really do better than the maximum possible coverage on these benchmarks. And then there's other few benchmarks where CLI-reduce doesn't get the same coverage as CLI-base, and I'll discuss these shortly. So overall, if we just sum up all the percents, just to give you an idea of how they look in aggregate, just add the percentages across the board as a total 156%. If you just look at the increases are greater than 0, it's 221. And the increase is less than 0, it's negative 65. And the average increase is about 3.8%. So these are the 10 largest benchmarks in terms of code. And the purpose of this slide is to show that the speed ups and coverage increases aren't limited to the small benchmarks. They're actually, even for the largest ones, you see quite a bit of speed ups and coverage increases. So on some of these benchmarks, as indicated before, CLI-reduce wasn't able to reach CLI-base. And there's two reasons for that are easily fixable, but we just haven't gotten to them yet, just because of time. So the first one is that on about half of them, the constraint solver ends up taking up, the symbolic execution ends up getting stuck in a constraint solver. So some query gets sent to the constraint solver and it just sits there for like the entire hour without making any progress elsewhere. So there's an easy fix for that, and was just to put a timeout, but we just haven't done that yet. And the other reason why it doesn't do well on those specific benchmarks is that is the precision in how we calculate dependencies. So you saw, for example, that we used sound static LT analysis, which is notoriously imprecise. And we plan on fixing that in the next few months. So this is a short slide on the closest related work. So there's some work from Patrice Godefroy in compositional dynamic test generation where he tries to avoid executing functions over and over again in symbolic execution. So he just generates a summary for them, uses those summaries. There's also another predecessor paper from our group that introduced the idea of comparing a state to previously executed states Yeah, the key difference between our technique and this other paper is that we're far more precise because we track the dependencies between variables and how they flow with each other. And this is critical to get these kinds of speedups. And the last piece of work is efficient state merging, where instead of pruning states, they just merge states together. So this is also a great technique. In fact, having a redundant state detector in combination with state merging, you probably get much better speedups than each of them separately. So they're very complementary to each other. Okay, I'll take questions if anyone has any.
I have a question. When you are pruning new inputs, do you compare with all previous states?
Right, so we only compare a state to other states that have reached the same line of code only. It's actually unsound to compare it, or in the way our redundant state detector works, we can only compare a state to the states at the same program point.
Mm-hmm. So it reduces number of possible comparisons.
Right, it does, but it's actually necessary because if you can't just compare two different states from two different program points. It actually becomes unsound. You could actually end up pruning a state that will reach a new line of code. So that's why we don't do that. It's not for optimization, not to reduce overhead or anything like that. It's a necessary part of the analysis to maintain soundness. Yeah.
Dave Holland, Harvard University.
Hi.
So I just have a quick question. Since you haven't really said, to what extent is your analysis context sensitive?
So it's a dynamic analysis. Actually, it's actually also related to the previous questioner's comment. So the program points we compare, when you take two states and you compare them, we only compare not only at the same program point, but at the same context-sensitive program points. So if, for example, you're in memcopy and two different states at memcopy, you try to compare them to each other and you prune, you could actually end up being unsound. So what we have.
So you are context sensitive?
Yes.
Okay.
Yeah. When you compare your tool with the baseline one, you let them run for 1 hour and then you basically look at the coverage. Did you try maybe let them run for, let's say, 30 minutes or 2 hours and then see how it compares to?
We haven't run that experiment. So we took the approach of just looking at what the original CLE paper did. We were thinking that was the best setup for CLE base, and we're just trying to benchmark how CLE reduce is with CLE base. But that actually may be an interesting experiment to run.
Thank you.